Hello, hello. So let's get started with the species mass transport, or we can say this as conservation of species mass. Okay. So, but first we have to know the different measures of concentration. So in that we have mass units and molar units. In mass units we have first mass concentration of A, which is equal to rho A, which is defined as mass of species A divided by the volume of the total mixture, total volume of the mixture. Then we have a mass density given by denoted by rho, which is equal to total mass of the mixture divided by the volume of the mixture. Obviously, you can see that rho will be equal to rho A plus rho B. Then we have a mass fraction of A. This is something which you already know, which is denoted as WA is equal to mass of A divided by total mass of mixture. And you obviously see that WA is equal to rho A by rho. Okay, volume term will get cancelled and you will get WA equal to rho A by rho. Moving on to molar units, we have a molar concentration of A given by Ca equal to moles of A by volume of mixture. And then we have the molar density, which is given by C, that is equal to total moles of the mixture divided by the volume of the mixture. Obviously, again, similarly, C equal to Ca plus Cb. And then we have mole fraction given of A, which is Xa, equal to moles of A by total moles of mixture. And that will be also equal to Ca by C. Okay, we'll move on to the next slide. Okay, so moving on, we'll discuss the constitutive relation in species balance, which is the Fick's law of diffusion. Okay, so what it basically states is that the species mass flux by diffusion is proportional to the concentration gradient. Okay, and JY, this is the relation. Okay, J is the mass flux of species A in the y direction. So JAY is equal to minus rho into DAB into dou by of WA. WA we know mass fraction of the species. DAB is called the diffusivity or diffusion coefficient. Rho is the mass density. We know that. And so basically we can see that the molecular species mass flows along negative concentration gradient. And the sign convention is such that the flux JY will be positive when the mass flowing along positive y direction. And similarly for other directions, that is in 3 dimensions, we can write down JY, JX and JZ as shown. And combining all these 3 together in vector form, we can write as JA, which is the total mass flux of species A due to diffusion, is equal to minus rho into DAB into gradient of the mass fraction of A. Obviously, Fick's law of diffusion is constitutive relation, and we have written this down for homogeneous isotropic cases because we have taken DAB to be the same in all directions. And it's called molecular diffusivity. DAB is molecular diffusivity. It has units of meters square per second, and actually it depends on temperature and pressure also. For gases, it varies as T to the power 3 by 2 and reciprocal pressure, for example. And if you see its magnitude in case of gas-gas mixture will be lesser than that of a liquid-liquid mixture. And this general form of Fick's law of diffusion can be rewritten as shown if mass density rho is constant. So that rho can be taken in, and we know that W into rho is equal to rho A. Okay, and obviously the same thing in vector form is represented over here. And move on to the molecular species flux of A in the next slide. Okay, so let us discuss the molecular species flux of species A in terms of molar units quickly, due to diffusion obviously. So this is the more general form, capital J star AY, meaning the molar flux of species A due to diffusion in the y direction is this quantity in LHS, that is equal to minus C into DAB into dou by dou of XA. XA is the mole fraction of A in the mixture. DAB we know diffusion coefficient, and C is the total molar concentration or molar density of the mixture. Now obviously if that C is constant, we can take it in, and the C into XA we know it will become CA. Okay, and therefore this is what we'll get. And the same for all directions, and combining to form a vector equation, capital J star is equal to minus C DAB gradient of XA is what we'll get. Okay, we're moving on. There is also a need now for defining average velocity. Before, till now we were the velocity that we were discussing had single meaning, but here we need to define a molar average velocity and a mass average velocity, because the mass of species A which is transported is given by that due to diffusion plus the contribution due to convection. So the flux of a species A with respect to stationary coordinates is equal to flux of A due to diffusion relative to average velocity that we will define in next slide. Okay, plus the flux of species A due to convection at the average velocity. So of course there is a need for this because in a mixture the two species if we have that we traveling at different velocities. Okay. Okay, so taking our discussion forward, we will quickly go over this definition of velocities and fluxes, namely molar and mass average velocities, and also mass flux and molar flux. So if you can see over here, Na, okay, Na is the mass flux of species A with respect to fixed coordinates. Okay, it is previously we saw Ja, right? That was mass flux of species A, but that was due to diffusion only. And let's say Va, this Va is the velocity of species A with respect to fixed coordinates. And we will define average of all velocities of molecules of species A. Va is basically average of all velocities of molecules of species A within a small volume. Okay, this is just for understanding. Now, Na is equal to rho A into Va. Okay, rho A is the mass concentration of A multiplied by this velocity of species gives us the mass flux of species. Is clear, right? And okay, this for y direction, x direction, z direction combined we can write in vector. Now we will define the quantity which is mass average velocity given by just v in normal velocity vector which we denote, that is equal to WAVA plus WBVB. VB is the velocity of species B in nature. VA is velocity of species A in nature with respect to fixed coordinates. W and WB the mole fraction we know. That is equal to rho A VA plus rho B VB by rho. This is clear, right? Because W is rho A by rho. Okay. And this can be written as, okay, rho A VA is nothing but Na. Rho A is Na. So Na plus Nb by rho. We have Na plus Nb by rho. Na plus Nb is the total flux of species A and B together divided by the mass density of the mixture. So here the weighing factor which we have considered while evaluating the mass average velocity is the Wa, which is mass fraction. We define mass average velocity V such that when it is multiplied by mass density rho, it should give us the total mass flux. Okay. Now similarly for molar flux, we can denote the capital N as molar flux of species A with respect to fixed coordinates, and then we have velocity of species A with respect to fixed coordinates is the same. Now the molar flux of species A is equal to the molar concentration of species A multiplied by its velocity. Okay, so here was rho A into V, here it is C into V. So now we'll define the molar average velocity given by V star. Okay, V star is equal to XAVA plus XBVB. So your weighing factor you can see is mole fraction. And now this can be written as CAVA plus CBVB by C. And we know CAVA is equal to Na, therefore Na plus Nb, which is total molar flux of both species divided by the molar concentration, total molar concentration of the mixture is this molar average velocity. So we have defined it such that when we multiply this V star by C, which is total molar concentration, we get the total molar flux. Okay, thank you.